No, that is the ions. The gold ones are the atoms, and we see the trend here. As you go across the periodic table, the size decreases. It kind of stays flat around the transition metals, but you can see the trend clearly here. The next thing we want to look at are the size of the ions. And so, for example, when you form an anion, like say fluorine to fluoride or oxygen to oxide, you can see that the size of the ion here, at least for anions, increases. And so about how much did it increase? So we went from 60 to 133 by adding an electron on there. So the size more than doubled here. And again, the size more than doubled here. In this case, we added 2 electrons. Did it triple? No, it just about doubled here. 3 electrons we add here, more than doubled. And so do we see this pattern down here? And it looks like we do here. Except when we go from sulfur to sulfide, we add 2 electrons. Did the size more than double? No. The size didn't quite double. It's less than doubling the size here. The same thing with the chlorine. Chlorine to chloride, we went from 100 to 181. And so if we just average this out, then what we can say is we can say that anions are twice as big as the parent atom, regardless of how many electrons it takes on. And so that seems to hold. And so anions, you just double the size. And so that means over here, which were the smallest atoms, these have pretty big anions because we're going to double the size. So iodine here, double it, or roughly double, in size. It comes out quite a bit bigger. Now, the cations here, when we look at the cations, what happened? And so we go lithium to lithium plus, 155 to 60, beryllium to beryllium 2 plus. This one was cut significantly. We went from 112 to 27. But let's see the overall pattern. So 190 to 102, 160 to 72, 235 to 138, 197 to 100. What would you say about the size of the cations, regardless of how many electrons we lose? It looks like the size of the cations is about half the size of the parent. And so when we form a cation, it's about half as big. And this is regardless of charge. So for example, if we go to chromium plus 2 at 73, so we go from 128 to 73. And if we go to chromium 3 plus, it goes to 62, so not a huge change there. And so it about was cut in half, right? 160. Again, here, it's about cut in half. And so the cations are about half as big as the parent. And so this does something strange to the sizes. As far as the biggest atoms go, they're at the bottom left. As far as the biggest ions go, the biggest ions are at the bottom right. And when we look at the anions, it turns out the anions, all the anions are bigger than the cations for the most part. There are exceptions, of course. Some of the smaller anions, 133. If you look at strontium 2 plus, 118, but rubidium plus is 152. But in general, the anions are bigger than the cations. The biggest anions, bottom right, and the biggest cation will be at the bottom left, and then the size decreases. Go up. All right, so that was the last periodic trend we needed to look at, the ions. All right, today we're doing Lewis structures. So do you, where did I leave off yesterday?
Covalent bonding at the start of this.
Covalent bonding?
We covered it.
Yeah.
About here? Covalent bonding and introduction. All right. So covalent bonding, we have a sharing of electrons, and here doesn't have to be an even sharing. We have something called a coordinate covalent bond. In a coordinate covalent bond, the only difference is this. When we look at a normal covalent bond, like hydrogen, oxygen here, a normal covalent bond, hydrogen donates 1 electron, oxygen donates electrons. So we have 2 electrons shared between hydrogen and oxygen on both sides. In H2, one H donates 1, the other H donates 1. And the same thing we see in Cl2. But in something like ammonium, if we look at ammonia, there's a lone pair here. And if we form ammonium, we have a hydrogen ion here. And what happens is hydrogen ion doesn't have any electrons to share, so ammonia will react with that hydrogen ion to form ammonium. And so in this case, both of the bonding electrons came from one atom, nitrogen. Hydrogen didn't contribute any to this bond here. And so we have a name for that type of bonding. It's called coordinate covalent or dative. So in ammonium, we have a coordinate covalent bond that formed up here. Once the bond is formed, you can't tell the difference. So once I have this bond formed here, these 4 bonds look exactly the same. There's no difference between them. The only difference is the origin, how it was made. But once it's made, it's the same as the other 3. And so that's an example. Hydronium here is another example where we take a water and add an H plus to form hydronium. There should be a positive charge here that was lost. Slide. So H3O plus. And so coordinate covalent bonds. Here. Here's another example of coordinate covalent bond. Here's ammonia, but in this case it's taking the hydrogen off HCl, not H plus. So here I can take that, leave these electrons behind here, so we form ammonium chloride. We don't need any water for this particular reaction. It's a coordinate covalent bond. We can have multiple bonds. We have multiple bonds when we don't quite get an octet. So when you look at this, there are only 7 electrons. 2, 4, 6, 7 electrons surrounding that oxygen. 2, 4, 6, 8. There's an octet around this carbon. And a 7 here. So we can get an octet by doubling the bonds here. So double bond, get an octet, octet, octet. Nitrogen, we'll have to triple up the bonding to get an octet. So there's a nitrogen-nitrogen triple bond. Oxygen, O2, we have to double the bond. A strange thing, the reason why there's a question mark here is because a strange thing happens with oxygen. When we look at oxygen, it looks diamagnetic. It's diamagnetic because we have 2 lone pairs, 2 bonding pairs. Everything's paired up. But this is liquid oxygen. If you take liquid oxygen and pour it into a magnetic field here, the liquid oxygen gets trapped by the magnetic field, meaning that if it were diamagnetic, it'd be weakly repelled and just flow through. But this is attracted to magnetic fields, telling us that oxygen is paramagnetic, not diamagnetic. And so it turns out that this structure is not correct. This is the correct Lewis structure, but Lewis theory, this is incorrect. Well, if Lewis theory or Lewis structures cannot predict this, then we should abandon it. But it's not abandoned because Lewis structures, they're easy to do. And so there are some limitations to it, though. And so we don't completely abandon it, we still use it. Because it gives us, for the most part, correct structures. And once in a while it's off, though. We aren't really going to get into it that much. All right, let's go on polar covalent bonds and electrostatic potential maps. What we're seeing here is that the electron cloud distribution can be uneven sometimes, and we have these electrostatic maps here. So this would be ammonia, and this is the electrostatic map of ammonia. What this electrostatic map is showing is it's showing the entire electron cloud for the molecule. And that electron cloud, you know, it depends on how close you want to get. You know, if you get closer, the potentials intensify. As you get further, the potentials but you know, it's a standard. We go this as far as the surface goes, and then we look at the surface itself. There's a color coding here. So red areas are, as we said, did I talk about this earlier? Right? Electron rich or electron poor regions. Electron rich. So the red area is electron rich by the nitrogen. And the blue areas are electron poor. This would be a solid surface. This is a transparent surface. So you can see the hydrogens would be electron poor, whereas the nitrogen would be electron rich. This particular one. It's transparent, but the molecule, you know, we're thinking about it bigger. So we can see it here. We can see the different types of bonding, the result depending on this. If you look at chlorine, chlorine's green, so the electron clouds spread pretty evenly throughout the chlorine molecule. And so what we call this bond is we call it a nonpolar covalent bond, Cl2. When we get to HCl, we can see that there's some polarization, that is, some distortion to the electron cloud. And so the electron cloud's being pulled closer to the chlorine. Chlorine's more electronegative. And so there's a buildup of negative charge density here, although it's hard to see. And then there's going to be a buildup of positive charge density here because the electron cloud is being pulled towards the chlorine. And so more density there. In sodium chloride, it's highly polarized here. You can see that the chlorine pulls much of the density towards it right there. In fact, sodium chloride is so polar, you know, when we get to something that's that polar, we start to call it ionic rather than covalent. In fact, when do we start calling things ionic, you know, and stop calling them covalent? Well, we look at electronegativities, and we look at the electronegativity difference, delta En, which is what I like to call it. And so I'm going to skip all this. What we're looking at is we're looking at the electronegativities here. Fluorine has the highest. Did I talk about electronegativities? No, I talked about electron affinities. What were electron affinities?
Whether you would like to accept an electron.
Ability to attract and hold an electron, yeah. And what has the highest electron affinity? Chlorine. Right. But as far as electronegativities go, chlorine's not at the top. In fact, chlorine's just a 3O. Fluorine's a 4O. And so what's the difference between electronegativity and electron affinity? Well, for electron affinity, we're looking at holding on to the electron. For electronegativity, we don't care about holding on to it. We just care about the attraction part of that. Ability to attract electrons. And fluorine's going to be the highest. Here. Followed by oxygen, and the nitrogen and chlorine look to be tied here. The lowest electronegativity would be francium at 0.7. So what we're going to do is we're going to look at the electronegativity difference. Electronegativity difference is how strongly the atom can attract electrons. Well, when we look at the electronegativity differences, we can plot it out here on a chart. And what this is showing is it's showing electronegativity difference versus percent ionic character. Percent ionic character is how ionic is that bond. In fact, there are just two extremes here. There's going to be ionic or covalent. So, well, it turns out that it depends on the difference in electronegativity. So, so from about 0 to about 0.5, you know, how much ionic character? Very little. If there's very little ionic character, that means that the bond is pretty much covalent. As we go on, we see the bonds become more and more ionic. Like, for example, lithium fluoride is highly ionic. And their electronegativity difference becomes greater. And so the biggest electronegativity is 4.0, the smallest is 0.7. And so the biggest potential difference in electronegativity is 3.3. Around here. You might have memorized this. We put some cutoffs. So if the electronegativity difference is between 0 and 0.5, we call it a nonpolar covalent bond. If the electronegativity is between 0.5 and 2, we call it a polar covalent bond. If the electronegativity difference is greater than 2, we call it a ionic bond. That's what we call it. Did you have to memorize those in Chem 4? Yeah? Some of you? Some of you not. Well, you know, those are just crude way to estimate, because look at the spread. For example, if we look at the percent ionic character, you know, from calculations, or from most likely those are from calculations, or actually you could do some measurements. And let's say if we have a delta En of here, then if we look at HF has about 40-something% ionic character. Whereas, well, HF, we would call that a polar covalent, correct? Polar covalent. But let's go to something like lithium or cesium iodide. If we look at cesium iodide has a greater difference in electronegativity or smaller difference in electronegativity? Smaller. And therefore, if HF is polar covalent, then cesium iodide should be even less polar because it has an even smaller electronegativity difference. Is that correct? That's correct, but if you look at how ionic, look how ionic it is. It's like 75% ionic. And so what we're seeing here is the spread. If I have a delta En of this, the percent ionic character can vary from anywhere from 40 to 80%. 40 to 80%, which is huge. That's a huge spread. And so how accurate is that? You know, if somebody told you, well, if the delta En is greater than 2, we call it ionic. How accurate is that? Or if the delta En is between 0.5 and 2, we call it polar covalent. Well, would you call cesium iodide polar covalent? I wouldn't call cesium, I'd call cesium iodide ionic. Well, why would you call it ionic? Because its delta En is less than 2. Shouldn't we have a delta En greater than 2 to call it ionic?
Yes.
Yes. And so those numbers, you know, those numbers, would you call that a law? The law of nonpolar covalent, polar covalent, and ionic? No, there's no way you would call it a law, because that equation and those cutoffs are very arbitrary. And so rather you just call it general guidelines. I wouldn't even go as far as to call it a rule. You know, a rule would be at least a little more consistent than this. This is not that consistent. And so it's just estimating is all it is. And so here, what we're going to do is this. In general, if we have a metal and a non-metal, we should consider it ionic. That is, if we have a metal and a non-metal, it looks like it's going to be greater than 50% ionic, therefore we should call it ionic. Now, if we have a non-metal and non-metal, then it could be non-polar covalent or polar covalent here. And that's kind of our guideline there for this. Because what do you think the R squared, if I look at the red, if I look at the red here, what do you think my R squared is? The red is supposed to fit all this data here. What do you think my R squared is? 0.9? 0.8? 0.6? Yeah, more like 0.6. It's a pretty bad correlation, isn't it? Yeah. Well, that's delta En in ionic character. And so the best would be just to do calculation or something else. Here we can see it though, as the delta En grows, if we look at this, we see the bond becomes more polar. And so chlorine's fairly electronegative, bromine's less, iodine's less. And over here, you know, HI is looking almost non-polar. Look how green both sides are. Both sides are pretty green, indicating that, you know, the electron cloud isn't really polarized one way or the other. It's more symmetric, more evenly distributed. And so HI is closer to non-polar covalent, whereas when we go over here to HCl, this is looking much more polar covalent. You can see the electron cloud being distorted. Even though the electron cloud looks the same, I'm looking at the colors here. And the colors are definitely showing that the hydrogen is becoming more positively charged. And so we can see that here, you know, so if we look at Cl2, and we're looking at the cloud here, it's looking pretty symmetric. And then let's go down to HCl. If we go to HCl, what's delta En for HCl? And so let's just take a look at the electronegativities here. And so if I look at the electronegativity of H, electronegativity of H is 2.1. 2.1 positions it between boron and carbon in terms of electronegativity. It's kind of in the center of the periodic table. And so H is 2.1. Cl is a 3.0. So 2.1, 3.0, the difference is 0.9. 0.9 would place it where? Let's take a look here. 0.9 would place it here. So what should we say? That is, well, it's about, what, 20%? Roughly 20% ionic character, 80% covalent character, which means that we'll call it polar covalent. And so this would be a polar covalent bond. In other words, what we're imagining is a tug of war. And so chlorine's a 3O. 3O versus a 3O, it's going to be a tie. But here we have a 2.1. A 2.1 versus a 3O. The 3O is stronger. And so the 3O is going to polarize some of the electron cloud towards it. And so this is going to be more red. This is going to be more blue. All right, then let's go to potassium chloride. If we go to potassium chloride, what's potassium's electronegativity? Potassium is a 0.8. And then chlorine's a 3O, which means a 0.8 and a 3O is going to give it an electronegativity difference of 0.8 and 3O gives it an electronegativity difference of 2.2. And so at 2.2, this is supposed to be 2.2 here. though it looks off because this is 2.5. Be back over here. A 2.2, we're going to call it ionic because it has delta En greater than 2. But there are some things that have delta Ens less than 2. So for example, lithium iodide. Would you call lithium iodide polar covalent, or would you call lithium iodide ionic? I would call it ionic, even though it has a delta En closer to 1.6 or 1.5, right? Be ionic. And so here, metal and non-metal.
Now, where are those numbers derived from? The electronegativity numbers?
Where are the electronegativity derived? These numbers here? These ones? These ones are derived from Z effective. You know, Z effective is the outermost charge, the electron fields. You know, and so these numbers are derived from Z effective, essentially. But these are what we call, and this is not written here. This is what we call Pauling's electronegativity scale. And Linus Pauling came up with these. He was a Nobel Prize winner. He's most famous for vitamin C. But I think he's a 2-time Nobel Prize winner. But he did a lot of studies on bonding. It turns out that these electronegativity aren't terribly accurate. These are just there for general use, and they're easy to use. But you know, if something's easy to use, sometimes it's oversimplified, which those are. Let's see if we can get some other electronegativity tables. Well, this doesn't come up. There are other electronegativity tables. Unfortunately, it doesn't pop up. That are much more useful. I just don't remember the names of the people that they're named after. Electronegativity is based on. Just all the basic ones. So there are issues with this. One of the issues is these numbers don't come out accurate. So for example, if oxygen has a double bond versus 2 single bonds, the electronegativity changes. Or it depends on the sulfur. You know, if sulfur has 2 bonds versus 6 bonds, its electronegativity is quite a bit different. And so there are other electronegativity tables which will give you a much more accurate picture of bonding. This is why this correlation is so bad. This correlation is so bad because it's based on Pauling, basically, electronegativity tables. If we look at some of these other ones, perhaps they'll become more. Although these are all diatomics. So anyway, so going back to this, now KCl is ionic. And so how should I draw the Lewis structure for KCl if we call it ionic?
K plus and Cl minus.
Yeah, it's going to be K plus and Cl minus, but how should I draw it? K should have no valence electrons, a bracket, and a positive charge. Cl minus it should have an octet with a minus charge. And that means that the electron cloud has been totally polarized. That is, Cl has pulled the electron cloud from potassium. But has it really completely pulled the electron cloud from potassium? And so if we take a look back here, what is the percent ionic character in KCl? The percent ionic character in KCl is about 80 or 90%. That means there's 10% covalent character. And so that electron cloud hasn't been completely stripped away from potassium. There's still a little bit of electron cloud around potassium. It's like 90% ionic. And this little bit of electron cloud, well, we ignore it because we're either going to draw it as covalent or ionic as far as Lewis structures go. And if it's polar covalent, then there are different ways we show that it's polar covalent. We don't usually draw electron cloud like this. There are other ways we show it. The other ways we show it is sometimes we'll write a delta minus and a delta plus to show that. And so the delta minus would be the red regions in the electrostatic potential map, and the delta plus would be the blue regions in the electrostatic potential map. So here. HI, let's see what the electronegativity difference on HI is, and what we would classify HI as. When we look at HI, the delta EN here is less than 0.5. If delta EN is less than 0.5, we would call it what? Non-polar covalent. And so HI would have an electron cloud that looks similar to Cl2. You know, there's just a slight polarization. A very slight polarization in the electron cloud. Now, which one's more electronegative, hydrogen or iodine? And so let's go back and look at Pauling's. If we look at hydrogen's 2.1, iodine is 2.5. So iodine is just slightly more electronegative. So there would be just a slight polarization towards iodine. But that slight polarization is negligible when you look at this. Can you see the slight polarization towards iodine there? Do you see any red buildup at iodine? No, it looks pretty non-polar to me. So a delta EN of 0.4 is not significant. It looks pretty non-polar. All right, so that's a little bit about bonding. We're going to come back to this later, but for us, what it means is this. It means, now how do we draw the Lewis structures? How we draw the Lewis structures depends. Am I going to treat it as ionic or am I going to treat it as covalent? Because I'm going to just have two choices for Lewis structures, ionic or covalent. Now, we could have done it based on delta EN, but we'd be wrong on certain cases. And so from Chem 4, you know, delta ENs between 0.5 and 2 would be considered covalent, but would you write lithium iodide as covalent? You know, or would you write it as ionic? What would you do? You know, lithium iodide, in other words, would you write lithium iodide like this? Or would you write it like this?
Like that. Like this.
Which one, the first one or the second one?
The second one.
The second one for sure. You know, we would treat it, look at, lithium iodide is more than 50% ionic, right? It's more than 50% ionic, which means it's more ionic than it is covalent, so we better write it like that. But the delta EN is only 1.5. Well, HF has a much bigger delta EN. The delta EN of HF is 1.8. Are you going to write it as ionic or are you going to write it as covalent? You're going to write it as covalent, right? And so the whole delta EN stuff we don't use to really base our Lewis structures. We're just going to base it on metal and non-metal is going to be ionic, unless it's ammonium. If we have like ammonium chloride, it'll be Yeah. Or we're going to base it on nonmetals. Okay, so HF, we would have picked, even though it's delta En. For lithium iodide, we draw it like this. HF, we're going to draw it like this. Even though the delta ENs are opposite. Okay. All right, so let's talk about drawing Lewis structures. Just briefly go through the rules. Writing Lewis structures, all the valence electrons. So we just count up the valence electrons. Usually the electrons are paired. Each atom requires an octet, except hydrogen requires a duet. Sometimes multiple bonds are needed. And so here we have central atoms, which are red, or bridging atoms, which are red. Terminal atoms here are shown in blue. And so here we have 3 central atoms, and the hydrogens are all terminal. Hydrogen atoms are always terminal. Central atoms generally have the lowest electronegativities. Carbon atoms are always central. Central meaning, if it can be. Sometimes the carbon's at the end. Generally, structures are compact and symmetrical. Not always, just generally. Okay, here's the rules for drawing out Lewis structures. And so we can see an example here. And so this structure looks pretty good. But one thing that we have to know is this. Oxidation states, do you remember that? What is an oxidation state? How is it defined?